Every year, new icebreakers are launched around the world, giants capable of cutting through ice several meters thick. These are ships whose mass can exceed 20,000 tons, more than the weight of an entire stadium filled with people. But how is this steel beast born from 1,000 metal blocks? What does the moment look like when a multi-story crane, with millimeter precision, installs a piece of the hull weighing hundreds of tons? And what happens when the ship's bow first cuts into an ice field, and the hull shudders from an impact similar to an earthquake? In this video, you will learn what is not shown to the public, from digital ghosts in design bureaus to the moment of truth when an icebreaker meets its first ice. Watch until the end, because a secret that few know awaits you. It all begins not with the roar of hammers, but with the silence of a design bureau. Before a single piece of metal is cut, thousands of engineers spend years at computers. They create a detailed three-dimensional model of the future vessel. This is a digital twin, where every screw, every weld seam, every meter of pipe is calculated. Using powerful computers, they simulate the most extreme situations. How the hull will interact with ice of different thicknesses. How the ship will behave in a hurricane. How it will withstand a collision with a multi-ton hummock. These are virtual crash tests, where the cost of an error is only processor time, not human lives. Only when every aspect of this digital ghost is perfected are the drawings sent to the workshop. Icebreakers are not built whole, like a model ship in a bottle. They are assembled from giant blocks, like a colossal Lego set. In huge workshops, the size of several football fields, the cutting of steel begins. For icebreakers, special low-temperature, high-strength alloys are used. Ordinary steel in the Arctic cold becomes brittle as glass and can crack from a strong impact. But this one retains its ductility and strength even at a temperature of -60 degrees Fahrenheit. The sheets of this steel can be incredibly thick. If a regular ship has a hull thickness of less than an inch, then an icebreaker in the so-called ice belt, the area that contacts the ice, can have a thickness of 2 inches or more. This is thicker than a bank vault door. Plasma cutters, controlled by a computer, with a hiss and showers of sparks, cut thousands of parts of the future hull from these sheets. Then these parts are welded into sections, and the sections into huge multi-story blocks. Each such block is already a finished part of the ship, for example, a piece of the engine room, or several cabins, already with part of the pipes and fasteners. Every weld seam here is a matter of life and death, so it is checked with X-rays and ultrasound to ensure the absence of the slightest defects. A symbolic moment arrives, the laying of the keel. On a huge construction site called a slipway or a dry dock, the first central block is installed. This is the spine of the future giant. And to this spine, like ribs to a spine, other blocks begin to be attached. Giant gantry cranes, looming over the entire dock, come into play. With incredible precision, they lift these multi-ton pieces, weighing hundreds of tons each, carry them through the air, and with millimeter precision, set them in place. Welders, resembling astronauts in their protective suits, connect these blocks into a single, monolithic hull. Gradually, day by day, a giant steel beast grows from these separate pieces, and its shape is its main weapon. The bow of an icebreaker is not sharp, like a regular ship's. It has a special, spoon-like shape. It doesn't cut the ice. It crawls onto it, and then, under the action of the colossal weight of the entire vessel, and this can be from 15 to 20,000 tons, it simply breaks the ice, like a person stepping on thin ice on a puddle. Its bottom is rounded, without a protruding keel, so that after breaking the ice, it can easily push the fragments aside and not get stuck. While the hull is growing, the heart is installed inside. the power plant. An icebreaker needs not so much speed as colossal, unstoppable power and torque. Therefore, most modern icebreakers are diesel-electric. Imagine that a whole power station is inside it. Several giant diesel engines, each the size of a bus, turn generators, producing megawatts of electricity. This energy is then supplied to huge electric motors located in the aft part of the vessel, which directly turn the propellers. This scheme allows for maximum power on the propellers instantly and very precise regulation. The total power of the power plant can reach 50,000 horsepower, enough to power a small city. The propellers of an icebreaker are also a work of art. They are made of super strong stainless steel, have a huge diameter, and thick blades like the wings of an airplane, capable of withstanding impacts from ice flows weighing tons. When the hull is assembled and the main equipment is installed, the moment of birth arrives, the launch. If the ship was built in a dry dock, the dock is simply slowly filled with water, and the giant ship smoothly floats off its supports. If it was built on an inclined slipway, it is much more dramatic. The supports are cut, and the multi-thousand-ton machine, gaining speed, slides into the water with a creak and a roar, raising a huge wave. And so, this giant for the first time sways on the waves. But it is still far from ready. It is just an empty steel box with engines. It is towed to a fitting-out quay, and here the most complex part begins: the outfitting. Hundreds of miles of electrical cables, thousands of meters of pipes for water, fuel, sewage, ventilation are laid throughout the ship, forming its circulatory and nervous systems. Living modules, wardrooms, a galley, a medical unit are installed. Navigational equipment is mounted on the captain's bridge. Radars, sonars, satellite systems, powerful deck cranes, scientific equipment, a helicopter pad are installed. The entire ship is covered with a thick layer of thermal insulation. And then the time for the final exam comes. The icebreaker goes out into the open sea, away from the shore. On board, not only the crew, but a whole army of engineers, representatives of the shipyard, classification societies, and the customer. Each of them with their own notebook and a list of hundreds of items that need to be checked. It all starts with the basics. Full ahead. The command sounds from the bridge. The engine room comes to life, the diesel generators go to full power, and the giant propellers begin to accelerate the multi-thousand-ton machine. Engineers with sensors check everything: hull vibration, engine temperature, pressure in the fuel systems. The vessel accelerates to its maximum speed on clear water, which is usually not very impressive, about 17 knots. Then the command, "Stop engine." And everyone watches how many miles this giant will need to come to a complete stop. This is called the inertial coasting. Next, maneuverability. Hard to port. And the rudder is turned to the maximum angle. Everyone watches how large the turning circle will be. That is, how wide a circle the icebreaker will describe at a full turn. They test reverse, reaction speed to commands, the work of the autopilot. Every system, from the large engines to the small pump in the toilet, is turned on and off, checked under maximum load. They even conduct a so-called blackout test. They deliberately turn off the main power to check how quickly the emergency diesel generators will start and restore the operation of vital systems. Only when every item on the long list is checked off. But all this was just a warm-up. The real exam is ahead. Winter comes, and our icebreaker, fueled to the brim, heads north, towards its true calling: the first encounter with the ice. This is the moment of truth. The captain directs the vessel straight into an ice field. From the bridge, you can see the horizon turning into an endless white desert. First comes young, thin ice. The icebreaker passes through it like a knife through butter, with a light rustle and crackle. But then the ice gets thicker. And so, the vessel at full speed crashes into real, multi-year ice several feet thick. A deafening blow sounds, shaking the entire hull. This is not like a collision. It's like the sound of an earthquake. The whole ship vibrates, dishes in the cupboards rattle. The specially designed bow crawls onto the ice, and under the weight of thousands of tons of steel, it breaks with a loud crack, spreading giant cracks. The fragments, the size of cars, scrape against the sides with a grinding sound. And so, meter by meter, the icebreaker makes its way. Special sensors, installed throughout the hull, record the pressure that the ice exerts on the hull and transmit the data to the engineers. They check whether the real loads correspond to those calculated in the computer models. It returns to port for final adjustments. Every hour, over 100 million gigabytes of data are transmitted worldwide. But few people know that almost all of this traffic passes not through satellites, but through cables laid on the ocean floor. They withstand depths of 26,000 feet, pressures of hundreds of atmospheres, and work for decades without repair. How do you create a cable that isn't afraid of salt water, marine life, and time? Why is it not just wire inside, but laser fibers and an invisible gel? And most importantly, what dangerous mistake does the deep not forgive? Watch until the end, and you'll find out what they don't even write in technical reports. For the internet to cross oceans, a cable is needed that can withstand pressure, salt water, marine life, and decades of operation without repair. It all starts with the central core, a copper or aluminum conductor through which the main signal travels. Large ingots of purified metal are melted and passed through drawing machines, which repeatedly pull the material through narrowing dies, reducing the diameter to a few millimeters. At this stage, a perfectly round cross-section is formed, one that has no micro cracks or air pockets. After drawing, the wire undergoes heat treatment. It is heated to a precisely set temperature to relieve internal stress and make it more flexible. Then it is cleaned of oxides, often by a chemical method or using abrasive rollers. The output is a shiny, smooth, almost flawless wire. It is checked automatically for diameter, resistance, flexibility, and surface purity. The wire must withstand kilometers of bending and work without failure, even at depths of several thousand feet. Depending on the type of cable, the wire is either used as a single solid conductor or is twisted from several thinner strands, which increases flexibility and protection against breakage. Once the copper or aluminum conductor is ready, it is immediately fed into an extrusion line, a long machine resembling a tunnel. Inside, polyethylene heated to 482 degrees Fahrenheit, which melts into a thick, viscous cream. The conductor moves along a conveyor and enters the extruder head, where the molten polymer precisely and evenly flows around the metal, like a second body. Every millisecond is important here. Too slow, and drips will form. Too fast, the polyethylene won't have time to adhere. Immediately after this, the cable enters a bath of cooling water, where the polyethylene layer quickly solidifies, tightly enveloping the conductor. The entire surface must be smooth, without a single bubble or crack. This is the first line of defense against moisture. After cooling, inspection, lasers measure the insulation thickness, and cameras check the surface. If anything is even slightly off, the cable is cut and reprocessed. The next stage is the application of a hydrophobic gel, which acts as an invisible protector. This thick, viscous compound fills all the voids inside the cable, envelops the optical fibers, and creates an internal shield against moisture. In a special chamber, the cable passes through a system of nozzles or rotating heads that evenly apply the gel to the central part and in the space between the fiber elements. The gel resembles a transparent lubricant. It doesn't dry out, freeze, or dissolve in water, even at a depth of 26,000 feet under a pressure of hundreds of atmospheres. Its main property is to repel water. If the cable's sheath is ever breached, the gel instantly spreads and prevents moisture from penetrating inside, not letting it reach the sensitive fibers. At this stage, it's also important that there isn't too much gel. Otherwise, it complicates the further laying of layers, and not too little. Then, the protection efficiency drops. Computers precisely regulate the dosage, and operators visually check the filling and uniformity. After application, a short cooling and stabilization. Now the cable is ready to receive its optical heart, the fiber threads that transmit light from one continent to another. These fibers, usually from 4 to 12 of them, are first grouped into modules. Each module is a flexible capsule with several fibers inside, providing additional protection. The modules are very carefully arranged in a spiral around the central conductor. This configuration allows the fibers to bend without tension, especially during winding and laying the cable at sea. To keep the fibers in place, they are fixed in a bedding of gel that was applied earlier. There is no glue, only a tight fit and a flexible structure. It's important that no fiber crosses another, breaks, or shifts from its place. The work is almost like jewelry making, although it's done on a conveyor. Afterward, a continuity check of each fiber. A laser beam is sent through them. Even a micro crack or a bend will cause a failure, and the fiber won't pass inspection. If everything is fine, the structure moves on to the next stage: additional insulation and reinforcement. First, an additional polymer layer is applied over the optical fiber structure. Often it's high-density polyethylene or another flexible, waterproof material. It protects against mechanical damage, friction, and moisture. This is again done in an extruder, similar to the one where the first insulation layer was applied. The cable passes through molten polymer and immediately enters a cooling bath. After cooling, the cable enters the steel wire braiding section. Machines evenly lay steel rods or tapes in a spiral around the already insulated core. In shallow water areas, this armor is thicker to protect against anchors, fishing nets, and shark teeth. At depth, the armor is thinner or absent altogether. After reinforcement, another outer polymer sheath may be added, which seals the entire structure. Operators carefully inspect the cable surface, checking for uniform thickness, no abrasions, burrs, cracks, or armor misalignments. Then, automated tests. Lasers scan the thickness, cameras capture every millimeter. Light pulses are sent through the fibers again. The signal must pass without delays or losses. If a defect is found at this stage, it is cut out and both ends are joined using a special technology, creating a sealed splice joint. After inspection, the cable enters the marking section. Here, information about the batch, production date, cable type, and its purpose is printed on the outer sheath. Often, every few meters, so it's easy to identify the cable even during laying on the seabed. And finally, winding onto spools. These are giant drums with a diameter of up to 13 or 16 feet, which can hold up to 8,200 feet of cable. Each turn must lie flat, without twists, and with uniform tension. Automatic systems regulate the speed and tension force, and operators monitor each stage. If the cable is intended for installation at sea, the drums are immediately sent to ships, where they are installed on the deck. If not, they are stored in special warehouses with humidity control, because even minor corrosion can be fatal. Every year, over 2 billion feet of rope are produced worldwide. But how does a formless cloud of fibers turn into a lifeline capable of holding a tanker, a crane, or a hurricane? We will dive into the depths of rope manufacturing, where threads become muscles, where spindles spin at insane speeds, and the temperature reaches 450 degrees Fahrenheit. You will see machines that look like steel spiders, weaving ropes with micron precision. And if you watch until the end, you'll learn what one detail can destroy even the strongest rope. It all starts with yarn. Yarn is not just a thread. It's the foundation of almost everything we wear, pull, tie, and hang. It is the beginning of the story of any cable or rope. But even earlier, it's just scattered fibers. Fluff, thin strands, like a spider's web. How does this messy mass turn into a resilient, strong, solid thread? It all begins with preparing the fibers. If it's synthetic, for example, polyester, nylon, Polypropylene, it's drawn from a melt, cooled, and cut into uniform lengths. Natural fibers, cotton, wool, linen, hemp, are cleaned, combed, and short fragments are removed. The goal is to obtain a soft, elastic mass in which all fibers run in the same direction. Next comes spinning. This is a true art. The fibers are drawn, thinned, and twisted into a thread. Everything happens on large spindles or rotor machines with incredible precision. The character of the thread depends on the strength of the twist. A weak twist will make it fluffy and soft. A strong one, resilient, almost springy. This is exactly what's needed for ropes. Yarn is often made of several threads. For example, 2 or 3 threads are joined and twisted together again in the opposite direction. This stabilizes the structure and prevents it from unraveling. In thick technical ropes, there can be hundreds of such mini threads. Next comes finishing. We don't see it, but it's important. Anti-static additives, thermal stabilizers, impregnation against moisture or bacteria. The yarn can be heat set, meaning it's heated and cooled under tension, so it remembers its shape. And here it is, the finished yarn. On bobbins, wound into dense cylinders. It can become fabric, or it can become the sole of a rope that will hold a seaport or a boat in a storm. A huge hall with rows of machines that look like mechanical spiders. From the bobbins on the upper tiers, thousands of thin, shiny threads are pulled. They are almost invisible, but create a net in the air, like a spider web shimmering under the light. And here the movement begins. Motors hum, spindles come to life. The threads fly off the spools and merge into one common ribbon. They seem to seek each other out, intertwine, embrace, and merge into a strand. The strands rush on, through tension rollers, through guides, until they reach the main part of the machine, the twisting unit. And here everything changes. Huge spindles rotate at an insane speed, so fast that their outlines are invisible. You can only guess the movement by the rhythmic gleam of the metal. The threads begin to twist into strands, like muscles building strength. All this happens in silence, broken only by the sounds of mechanics, a uniform hum, clicking, the rustle of fibers. The newly created rope muscles slowly descend, coiling into a spool. The silence in the workshop is replaced by a hum, resembling the sigh of a huge machine. Thin strands, like streams, converge at the heart of the process, the place where they will become one body. Dozens, even hundreds of threads, each separate, independent. But as soon as they pass through a system of rollers and guides, they become something whole. Because in a rope, everything is decided by balance. If one thread is weaker, it will break under tension. If it's stronger, the tension will be distributed unevenly, and the whole structure will go haywire. Here, everything must be like in a choir, synchronous, coordinated, strong. Next, the spindles. These aren't the small wooden spinners from fairy tales. These are steel giants that rotate at such a speed that they disappear from sight, leaving only a shining halo of motion. The threads fly into them like lightning bolts and come out already twisted, with tension inside, with an internal spiral of strength. One turn, a second, thousands of revolutions per minute. And now, instead of fluffy strands, before us appears a sinew that trembles from tension, like a string. You touch it and hear a ringing sound. You pull it and feel resistance. The rope is formed gradually. First, small threads are twisted into sub-ropes, then several such strands, into the core of the rope, and finally, the final twisting of the entire body. And at each of these stages, the angle of rotation, tension, thickness, and viscosity of movement are controlled. The rope must not only be strong, but also predictable, so that it doesn't stretch, doesn't twist inside out, doesn't break at a bend. Another magical thing is the spiral pattern. If you look from the side, each strand lies at an angle, creating a classic spiral. This is the law of engineering. Such a shape evenly distributes the load along the entire length, allowing the rope to work as a single muscle fiber. In a super thick marine rope, there can be 3, 4, or more such strands, and each contains hundreds of threads. In the air, there's a light smell of burning and oil, the rustle of fibers, the whistle of tension. The machines breathe, as if alive, and the rope, still damp, hot from friction, slides down, coiling into rings. It hasn't cooled yet. It still remembers the rotation of the spindles, but it already has shape, resistance, a heart. In factories in the US, where industrial ropes are made for ships, cranes, the military, or oil rigs, heat treatment is a mandatory stage. A rope, often 1 or 2 inches in diameter or more, passes through long heat tunnels, from 12 to 40 feet in length. Inside, the temperature rises to 250 to 320 degrees Fahrenheit, depending on the type of yarn. For heat-resistant synthetic fibers, like polyester or aramid, such as Kevlar, it can be even higher, up to 450 degrees. There's no open flame here, only superheated air and controlled tension. The rope moves slowly. In parallel, it's slightly tensioned. Not to break it, but so the fibers line up and remember their shape. It's similar to how a metal spring is heated and its coils are fixed. Each fiber, like a tiny spiral, acquires a stable state, reduces internal friction, and gets rid of residual deformation. This is heat setting. Without it, the rope behaves like raw dough. It stretches, unravels, twists under load. After, it's already trained how to behave under a weight of several tons. Its length is fixed, its resistance predictable. Sometimes ropes also undergo rapid cooling, meaning they are blasted with cold air or dipped in a bath. This helps freeze the fiber structure, preventing them from spreading out. The contrast, 400 degrees of heat and 50 of cooling, shocks the material and makes it even more resilient. Next, the rope is clamped between hydraulic grips, stretched over tens of feet, and subjected to a load of thousands of pounds. Literally, it's pulled to the limit. Digital sensors show every step of the tension: 2,000 pounds, 5,000 pounds, 10,000 pounds. The heavy silence of the workshop compresses as the rope begins to twitch. Each sample has a durability passport: maximum elongation, breaking point, residual deformation. If a rope fails, it's cut, analyzed, and the cause is studied. But even those that withstand need another layer of protection. Because ahead lies the real world, where water, salt, sun, metal fasteners, oil, and dust await them. Ropes are impregnated with protective compounds. Sometimes it's a polyurethane coating, a thin elastic layer that protects against moisture. Sometimes, ultraviolet stabilizers that prevent degradation under the sun. Some models get an anti-abrasive braid, a dense sheath of nylon or polyester that takes the impacts, friction, and wear. This is especially important for marine ropes. Salt corrodes the fibers, so their surfaces are often treated with special lubricants or waxes. For industrial conditions, chemical resistance to oil products, acids, and alkalis is added. One spool of rope contains from 600 to 1,200 feet. Such heavy ropes are often not wound, but coiled into hanks or onto large drums. Mooring ropes can be made to the required length right away: 50, 75, 100 feet without extra winding. Sometimes removable drums or wheeled winders are used, especially for mobile use, in the military, navy, or rescue services. Imagine a single chain link weighing 500 pounds and almost 4 feet long. Now, hundreds of such links connected together, stretching for 1,000 feet and weighing tens of tons. This isn't a movie set for a film about titans. This is the anchor chain of a supertanker, capable of holding a vessel the size of a skyscraper in a stormy sea. These giants of marine engineering don't work in the quiet of a harbor, but in the harshest conditions on the planet, under insane weight, with temperature fluctuations from -40 degrees Fahrenheit to positive 120 degrees, in salt water that eats away even the strongest steel. The first and most important step in producing anchor chains is choosing the right steel. For chains that must withstand tremendous tension in the open sea, low alloy structural steel with increased strength, impact resistance, and corrosion resistance is used. Its composition is selected so that the chain doesn't break from metal fatigue, isn't eaten away by salt, and doesn't crack from temperature fluctuations. factories receive steel in the form of solid rods or square bars, which look like long metal beams. Their diameter usually ranges from 3 to 6 inches, and their length up to 10 feet. The weight of one such piece is hundreds of pounds. All of this is stored in open assembly yards or inside large metal hangars, because the parts can withstand any weather conditions. Before being fed into production, the steel is checked for purity of composition. Even minor impurities can make the metal brittle. After quality inspection, the steel heads to the cutting lines. These are long automated sections where massive rods are transformed into blanks for links. Each steel rod is picked up by a hydraulic manipulator and placed on a guide. Then the main hero of this stage comes into play: a hydraulic guillotine press, or a cutting saw with carbide discs. The device calibrates the length, and when the blank is in the correct position, it presses with a force of thousands of pounds per square inch. With each loud thud, a characteristic crunch is heard, and a piece about 3 feet long is separated from the rod. This piece will become one link of the future anchor chain. A counter is displayed on a special screen or directly on the machine's body. It tracks how many links have already been prepared and whether the length needs to be adjusted. Each cut piece falls onto a conveyor or into a basket, where it is automatically checked by a laser scanner. If the system detects a deviation in length or an uneven end, that piece is sent back for remelting or trimming. The pieces that pass inspection are moved on to heating furnaces, where a bright orange heat of over 2000 degrees Fahrenheit awaits them. This temperature allows the steel to soften without losing its structural properties. It is there that the steel will become pliable and ready for bending into links. The cut pieces of steel, incredibly thick, rough, and heavy, are still cold, so they can't be bent at all. To give them the shape of a link, they need to be made pliable. The blanks are fed onto a roller line that leads directly into an induction or gas furnace. Inside the furnace, a dull hum can be heard, and the air is heavy, hot, and saturated with a metallic smell. The blanks lie on stands or are suspended on special rods and are gradually heated for 20 or 30 minutes. Externally, they begin to glow, first cherry red, then orange, and finally almost white. This is a visual indicator. The steel piece is ready for forming. As soon as the piece reaches the required temperature, it is quickly removed by a robot or a worker in a heat-resistant suit, because there's no time to waste. Steel loses heat very quickly, and if it cools by even 200 or 300 degrees, it will no longer be bendable. That's why the logistics of the hot chain production are so well coordinated. Every second matters. As soon as the 2000 degree Fahrenheit blank is removed from the furnace, it is instantly transferred to a bending machine, which looks like a hydraulic press robot with metal arms. These units can easily manipulate pieces weighing several hundred pounds, rotating, securing, and bending them with surgical precision. The essence of the process is simple at first glance. The blank is clamped between two massive forming rollers, one of which rotates around an axis. At the same time, the other presses with a force measured in tens of thousands of pounds per square inch. The steel yields and smoothly bends, forming a perfect ring with a diameter of up to 4 feet. While the metal is still soft, the ends of the link are joined, leaving the joint area slightly overlapped. Then the link is transferred to a welding station, where gas-shielded arc welding automatically begins. The temperature, over 5,000 degrees. The electric arc literally melts the edges and stitches them into one hole. The finished link is almost a part of the anchor chain, but before it is connected to others, the seam must be ground, heat-treated, and checked for defects. And only after this does it become part of a chain capable of holding a supertanker weighing hundreds of thousands of tons in a rough sea. While the link is still hot and pliable, it is immediately connected to the previous one, threaded through the already finished link. Only after this is the link closed, the seam welded, and this entire dual unit undergoes further processing. After all, it's impossible to open the previous link without damage, which would affect the chain's strength. When a link is welded, a noticeable seam remains at the joint, a bit rough, with weld spatter and metal buildups. In this state, It won't pass any tests, as it could catch on other links or even become a weak point under pressure. So, grinding comes into play. On a huge table, similar to a workbench for airplanes, lies a link weighing under 300 pounds. It is secured so that the seam is clearly accessible. An abrasive machine or an operator with a powerful grinding tool gets to work, which roars, sparks, and makes a characteristic buzz sound. The goal is to smooth the seam as much as possible, remove micro cracks and excess metal without damaging the main structure. Grinding takes place in several stages: first coarse, then medium, and finally, polishing. For this, discs of different grits are used, from 24 to 120, and sometimes even higher. After grinding, the link is blown with compressed air, cleaned of dust, and at this stage, it already looks like a perfect ring. But an external shine is not yet a guarantee of strength. So next comes heat treatment. Heat treatment strengthens the metal structure and makes the chain capable of withstanding insane loads in the depths of the sea. This is a complex series of thermal processes that are carefully controlled. First, the links are heated in furnaces to a temperature of 1,700 degrees Fahrenheit. Huge chambers, resembling metallurgical tunnels, hold dozens of links at once. Here, it is important to achieve uniform heating throughout the thickness of the metal, so that no internal stresses arise that could cause micro cracks. Next comes quenching. The links are rapidly cooled, usually in baths of oil, water, or a special salt solution. It is this temperature jump, from red hot to cold, that creates a hardened crystal structure in the steel. The result is increased hardness and wear resistance. But after quenching, the metal becomes too brittle. So the next stage is tempering. The links are placed back in the furnace, but at lower temperatures, approximately 1,000 degrees Fahrenheit, and held there for several hours. This allows residual stresses to be relieved, restoring elasticity and a balance between hardness and strength. Sometimes induction hardening is used, where heating occurs locally, only in the areas that experience the greatest loads. For example, the inner surfaces of the link where it connects with others. After heat treatment, the links are coated with an anti-corrosion layer that protects the metal from salt water, moisture, and rust. This is usually a hot dip galvanized coating, or epoxy paints, applied by dipping or spraying. Before this, the surface is degreased and ground again. The coating must lie evenly on every indentation, because the durability and safety of the entire structure depend on this. Hey, pull up a chair. You know that Starbucks cup? The one you see everywhere, the taste you can spot across a crowded room? Looks pretty straightforward, right? Just a little coffee, maybe some milk. But what if I told you that behind that simple cup is a global operation so vast, so precise, it's mind-blowing? We're talking about a supply chain that spans continents, a process built on incredible technology, and enough coffee moving every single day to fill. Well, let's just say it's a lot. Forget everything you thought you knew about coffee. Get ready to dive deep into the hidden industrial secrets of how Starbucks brings that coffee from a distant farm to your hands. The journey starts thousands of miles away, in places you might only dream of. The lush, vital coffee belt near the equator. Latin America, Africa, Asia. This isn't farming on a small scale. Starbucks works with millions of coffee farmers, building relationships that stretch back decades. They source massive amounts of green, unroasted coffee beans, demanding specific quality and flavor profiles unique to each region. Picture vast landscapes covered in coffee plants, where harvest isn't just picking fruit. It's a critical first step in a global race against time and quality loss. The beans are processed right there at the origin to remove the fruit and dry them, then packed into huge bags, hundreds of pounds each, ready for their epic voyage across oceans. One single bean in your cup could have traveled over 5,000 miles before it even hits the roaster. When these colossal shipments of green beans finally reach one of Starbucks' massive roasting plants, facilities the size of multiple football fields in places like Kent, Washington, or South Carolina, they face their first great challenge: cleaning. You wouldn't believe what can sneak into a shipment from remote farms. Twigs, stones, metal fragments, even lost tools. A single foreign object can ruin an entire batch, costing thousands. So, the beans are subjected to an intense cleaning gauntlet. Giant magnets yank out metal, screens sift out debris, and air currents separate lighter impurities. The most astonishing part? Advanced optical sorters. Cameras analyze every single bean as it flies past on a high-speed conveyor, using light and imaging to spot defects, discoloration, anything that isn't a perfect green bean. Rejected beans are blasted away by precise jets of air. They process literally millions of beans per hour, ensuring only the flawless make the cut. It's like a high-tech security checkpoint for coffee. Now, the transformation. Roasting. This is where those hard, green seeds undergo a chemical metamorphosis. Starbucks uses custom-built industrial roasters, monstrous rotating drums heated to blistering temperatures, often exceeding 500 degrees Fahrenheit. Inside, the beans tumble and dance in the intense heat. This isn't just burning them, it's a complex culinary science. The Maillard reaction and caramelization working in overdrive. Sugars unlock, acids develop, and hundreds of volatile aromatic compounds are created in seconds. It's a symphony of heat and chemistry. Precision is everything. Even a few seconds too long, or a few degrees off can shift the flavor profile entirely, turning a bright, complex coffee into something flat or bitter. Starbucks is famous for its signature roasts, from the light blonde to the intense dark. Achieving that consistent taste, bottle after bottle, region after region, across millions of pounds, is an engineering marvel controlled by sophisticated computer systems. But it's not just machines. Master roasters, artisans with years of training, monitor the process, listening for the distinct first crack and second crack sounds the beans make as they expand and release gases. They use their senses, smell, sight, even sound, coupled with data to fine-tune the roast. It's where human expertise meets industrial scale, ensuring the Pike Place roast you love tastes exactly the same in Seattle as it does in Shanghai, batch after batch. That level of consistent quality on this scale is almost unbelievable. Immediately after hitting that perfect roast point, the beans are practically glowing with heat. They have to be cooled instantly to stop the chemical reactions. Massive cooling trays with powerful fans suck air rapidly through the hot beans, bringing their temperature down in seconds. This quick cool down is vital. Slow cooling can damage the flavor. Then comes degassing. Freshly roasted beans naturally release carbon dioxide. It's a sign of freshness, but if trapped, it'll burst the packaging. Large facilities manage this with precision, sometimes resting beans in silos, or using specialized systems to control the gas release before packaging. It's all about preserving that peak flavor. Packaging is a high-speed ballet of engineering designed for one purpose: locking in freshness against coffee's worst enemies: light, moisture, and oxygen. Starbucks coffee bags are built from multi-layer, high-barrier materials that create an impenetrable shield. And look closely at the front of the bag. See that tiny plastic button? That's a one-way valve, a stroke of genius in packaging. It allows the CO2 gas naturally degassing from the fresh beans inside the bag to escape, preventing it from popping. But crucial for freshness, it absolutely prevents oxygen from getting in. High-speed automated lines weigh, fill, seal, and valve millions of bags per day with incredible speed and accuracy. The final guardian of quality? Starbucks' sensory labs. Located at roasting plants and headquarters, these labs are staffed by certified coffee cuppers. These aren't just people who like coffee, they're highly trained experts who can detect hundreds of flavor notes and defects. Every single roast batch is sampled. Cuppers evaluate aroma, acidity, body, and flavor, comparing it against strict global standards. It's a rigorous, meticulous process, like a tasting Olympics for coffee, ensuring that what ends up in your cup meets the exact profile Starbucks promises. This marriage of human sensory skill and industrial consistency is the final secret ingredient. So, the next time you take a sip of your favorite Starbucks coffee, remember the incredible hidden journey it took. From a tiny seed grown thousands of miles away, nurtured by farmers, transported across oceans, cleaned by optical scanners, transformed in roaring hot roasters, perfected by master artisans and computers, and sealed with precision in high-tech bags. It's more than just coffee. It's a product of a vast global network, incredible engineering, and a relentless focus on quality. It's a fascinating look at how something so simple in your hand is the result of massive industrial secrets. What part of this immense process surprised you the most? Let us know in the comments. It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to negative 260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create three separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. And 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about -260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Imagine this: red-hot metal, up to 33 feet long, being pushed with a dull roar into a massive rolling mill. No seams, no joints, just a perfectly smooth steel pipe appearing literally out of nowhere. These aren't scenes from a science fiction movie, but the daily work at one of the most unique factories in the world. How is it possible to create a pipe without a single seam? One that withstands pressure of hundreds of atmospheres and operates where other materials simply melt. Ready to walk through the scorching workshop and find out how true engineering perfection is born? Then let's embark on a journey to an amazing steel pipe factory. It all starts with cylindrical billets. Each one weighs 1 ton. That's like 3 smart cars in a metallic body. They are transported by rail or truck because other transports simply can't handle such a load. Each billet is secured on special pallets or in retaining clamps so it doesn't shift during movement. Upon arrival at the factory grounds, unloading is automated using cranes, manipulators, or hydraulic carts. The billets immediately go to the receiving area, where they are checked for compliance with technical specifications: chemical composition, shape, integrity. Before the hot steel becomes a pipe, it undergoes a truly dramatic inspection. Defects shall not pass. First, the billets get an X-ray. Well, not exactly X-ray, but something similar for metal: ultrasonic testing. You heard that right. The billet is coated with a conductive gel, like for a human ultrasound, and a transducer is moved across it. Special transducer ears shoot sound waves at a frequency of 5 megahertz. That's 100 times higher than submarine sonar. This is how they search for cracks and inclusions of foreign materials within the billets. The system builds a 3D map of defects with an accuracy of 1/100th of an inch. If it finds a saboteur, the billet is marked with red paint and sent to metal hell for remelting. Next comes the chemical analysis. For this, 5 or 10 metal samples are taken from each batch and sent to the factory laboratory. There, they use special spectrometers, devices that read the metal's composition using light emissions. The spectrometer determines over 12 elements in the composition in seconds. During the analysis, the sample is treated with an electric spark or a laser. This excites the atoms on the metal surface, causing them to emit light of different wavelengths. Each chemical element glows uniquely, so the device recognizes exactly which elements are present in the steel and in what quantities. How much carbon, manganese, chromium, nickel, or phosphorus. This analysis takes only a few minutes, but provides a complete picture of how well the billet meets technical requirements. If the composition isn't perfect, the batch might be rejected or redirected to other production lines. From 1 to 3% of billets are sent for remelting. Defective billets are sent to an electric furnace with a temperature of 2,900 degrees Fahrenheit, where the steel becomes liquid again. All the post-melting slag is used for road construction. 90% of defects are detected during the ultrasonic diagnostic stage. It's like finding a needle in a haystack in 10 seconds. The chemical analysis takes 17 seconds, faster than you order coffee at Starbucks. Quality control costs range from $50 to $100 per ton of steel. But it's better to overpay than to later have a well blowout due to low quality material. Quality control is the Karen's filter for steel. Only 97 to 99% of billets become pipes. The rest are sent for reincarnation. So when you hold coffee in a steel thermos, know this: its ancestors went through real metal special forces training. After checking the chemical composition, the cylindrical steel billets are delivered to the heating section, the place where a giant furnace stands. These furnaces are true giants, capable of holding over 1,000 billets simultaneously. To load the billets inside, massive automated cranes or special manipulators with heat shields are used. The billet is picked up using gripping mechanisms, large metal fingers or tongs that securely hold the heavy part. The crane carefully moves the billet to the open loading door of the furnace. At this time, The temperature inside can exceed 2,400 degrees Fahrenheit, so the entire process is maximally mechanized. People operate the machinery remotely from a safe cabin or control panel. The furnace has special guides or pushers that help place the billets carefully inside so that heat distributes evenly. After loading, the furnace doors are hermetically sealed, and gradual heating to the working temperature begins. In 2 hours, the steel transforms into a plastic mass. The billet becomes ready for forming, like melted chocolate. Next, the monster drill comes into play. It weighs 12 tons. That's like 2 elephants. The red-hot steel billets, massive cylinders, are removed from the furnace and delivered to a special rolling machine, where one of the most crucial stages of seamless pipe production begins, creating the hole inside. The piercing process looks impressive. The red-hot billet is placed on a special support ring in front of the piercing mill, where a thick, cone-shaped rod awaits it, the so-called piercer point or piercing mandrel. At this moment, immense force is at work. The billet is rotated between 2 conical rolls, spinning in opposite directions. The rolls don't just squeeze the billet, they create strong rotational and axial pressure, causing the billet to stretch along its axis, flowing around the piercer point. To avoid cracks or ruptures, the pressure and temperature during piercing are controlled very carefully. If the billet cools too quickly, or the pressure is distributed unevenly, it can break or lose the required shape. Therefore, the process runs without interruption, and with strict adherence to all parameters. This process is called the Mannesmann method, named after the German engineers who invented it in 1885. After the initial piercing, the resulting rough pipe is called a hollow shell or bloom. The wall thickness of the shell is approximately 2 inches. It still has uneven walls and may contain small defects, so the next stage is rolling and calibration, where the pipe is stretched, straightened, and brought to the required dimensions and wall thickness. The red-hot steel billet enters under giant rolls 5 feet in diameter. Under tremendous pressure, it's drawn out into a slender pipe up to 40 feet long, faster than you can blink. This is where the major league of precision reigns. Wall thickness is reduced from 0.8 inches to 1.2 inches, with a deviation of less than 4/1000ths of an inch. That's thinner than a human hair. And all this happens at staggering speeds of 16 to 49 feet per second, faster than Usain Bolt on his best day. It's like rolling out the thinnest pizza dough. Only instead of dough, it's a red-hot steel core. And instead of a kitchen board, there's a shower of sparks and the roar of the rolls. Next, fire gives way to ice. Well, not ice, but cooling. The workshop heat is 122 degrees Fahrenheit, so workers wear special suits as if preparing to conquer Mars. Meanwhile, the pipes gradually cool in the open air. Their temperature slowly drops to 570 degrees Fahrenheit to avoid deformation and cracking. When the pipe emerges from the fiery dance of rolling, it resembles an enraged dragon, powerful, but bent into wild spirals. That's when the 8-roll giant enters the scene, a mechanical Hephaestus that will forge perfect forms. Its rolls, stronger than the rocks of Olympus, bend the steel with a force of 500 tons. That's like putting 250 Land Rovers on the pipe. But this force isn't a destroyer, but a surgeon. It corrects curvatures smaller than the thickness of a hair. And then comes the time for lasers. They scan every millimeter, finding the smallest defects, invisible cracks, minor unevenness. And when they find something, plasma scalpels enter the game. 10 times hotter than lava, they cut the metal like cosmic lightning bolts. All that remains of the defects is smoke and legend. If the Colossus of Rhodes were made of such pipes, it would still be standing today.